Hello students, welcome to class. In my last class I talked about separation techniques. Today I'm also going to be talking about separation techniques where I'll be discussing the following separation techniques, which include separating funnel, magnetic separation, distillation, fractional distillation, sublimation, sieving, and chromatography. So we'll be starting with separating funnel. This is used to separate immiscible liquids. A good example of this is a mixture of petrol and water. Petrol and water do not mix together to form a single layer. The reason is because they are not polar and polar solvents respectively. Instead, they separate out into two distinct layers when they are added together. So, however, to separate the two layers, we make use of a separating funnel. The lower, denser liquid, or denser, which is heavier liquid layer, is tapped up, as you can see from the diagram, leaving the upper, less dense liquid layer in the funnel. In this case, water is the denser liquid layer, while the petrol is the less dense liquid layer. Next, we'll be talking about magnetic separation. This method involves the separation of magnetic substance from non-magnetic substance by means of a magnet. Industrially, it is used in steel industries to remove magnetic impurities from tin ores. So you can see a mixture of sulfur and iron filings can be separated by magnetic separation. Next, I'll be introducing you to a video that will give you a detailed explanation on distillation and fractional distillation.
In today's video, we're going to look at the two types of distillation that we can use to separate out mixtures that contain liquids. Let's start with simple distillation, which is used for separating out a liquid from a solution. For example, we could use simple distillation to separate pure water from seawater. Before we cover how it works though, we need to be familiar with the equipment. First, we have a flask that contains the solution, or the liquid mixture, that we're trying to separate. And the flask is sealed at the top with a bung, so that no gas can escape. We then put a thermometer through the bung so that we can measure the temperature inside the flask. Next, we have our condenser, which consists of a main pipe surrounded by a water jacket, which contains a stream of continually flowing cold water. with the water being fed into the water jacket at the bottom and coming out at the top. Then beneath the end of our condenser, we'll have some sort of beaker to capture our pure liquid. And finally, we're going to need some sort of heating device, like a Bunsen burner, which we place under the flask. Our first step is to heat up the mixture, so that the liquid that we want evaporates. As it rises to the top of the flask, the pressure will force it down the condenser. And because we're pumping cold water through the water jacket, the vapor will cool and condense into liquid form, which will then run down the pipe and collect in the beaker. So in our case, as we heat the seawater, we'll get more and more pure distilled water, until eventually all we have left in the flask is salt. Now imagine instead that we were trying this technique with a different mixture, one containing some different liquids, like methanol, ethanol, and propanol. Because these liquids all have similar boiling points, when we heat them, more than one of them will evaporate, and so they won't be separated into pure substances. In this case, we'd have to use a different technique, called fractional distillation, which is the main technique used for separating mixtures of liquids. The equipment for this is pretty similar, but instead of the gas passing straight from the flask into the condenser, the vapors have to first pass through a fractionating column, which has two key features. One is that it's full of little glass rods, which provide a really high surface area. And the other is that because the column is so tall, it's actually cooler at the top than it is at the bottom. To understand why this is important, let's imagine that we were trying to separate those three liquids that we mentioned before: methanol, ethanol, and propanol, which all have similar boiling points, although you don't need to remember them. And before we continue, just be aware that in real life, these would all be colourless, not green. We're just showing them as green to make it easier to follow along. Now, because methanol has the lowest boiling point, we'd heat the mixture to around 65 degrees first. This would cause the methanol to evaporate, and then rise up the fractionating column. It would then pass into the condenser, and condense into liquid methanol, which we would then collect in our beaker. However, just by chance, some of the ethanol, and maybe even propanol, would also evaporate. But as they rise up the fractionating column, and come into contact with all of those glass rods, which are much cooler than their boiling point, they'd condense back into liquid form, and fall back into the flask. This means that the only liquid that will get out the other side will be pure methanol. The next step would be to do the same thing all over again for ethanol, by raising the temperature to around 78 degrees Celsius, which would allow us to evaporate off the ethanol. At this point, all that should be left is the propanol. So we could just assume that what we have in the flask is pure propanol. Or we could raise the temperature again to boil off the propanol, just to make sure.
Next, we'll be talking about sublimation. But before I continue, I want to ask, can you tell me what distillation method is used for? Distillation method is used to recover a solvent from a solution. And you recall from the video that is also used for separation of mixable liquids with widely unduly far apart boiling points. Take note of that. Distillation is also used in gin distilleries and water distilleries for the manufacture of gin and distilled water, respectively. Now let's talk about sublimation. This method is used to separate a mixture of solids containing one which sublimes and one or more solids which do not sublime by heating the mixture. So when we say sublime, will mean solids which changes directly to vapor upon heating. So you take note of that. Examples of such solids are iodine, ammonium chloride, and naphthalene. This substance can, however, be separated from other solids by sublimation. So you take note. Next, I'll be introducing a video that will give you a detailed explanation on chromatography.
Chromatography. We'll take a look at how it's done, explain the theory behind it, like what the mobile and stationary phases mean, and also show you how to calculate RF values. Now, chromatography is a general analytical technique used to separate the different substances in a mixture so that we can then identify them. And there are actually lots of different types of chromatography. But the one you need to know about is paper chromatography, which can be used to separate the different dyes in an ink. The first step is to take a piece of filter paper and use a pencil to draw a line near the bottom of the sheet, which we call our baseline. Next, you want to add your sample of ink, which you think might contain lots of different substances, to the pencil line. Then we need to find a beaker and fill it with a shallow amount of solvent, like water or ethanol. We are now ready to start, and we can place the filter paper into the solvent. But importantly, we have to make sure that we don't submerge our pencil line and our spot of ink, which is why we made our solvent shallow. And if you're being careful, you should really place a lid on top to stop the solvent from evaporating. Then we just wait for the solvent to seep up the paper, and as it does so, the different dyes that make up our ink will dissolve in the solvent and move up with it. What makes this interesting, though, is that each of the different dyes will travel up the paper at different rates, and so they'll end up separating out, which tells us that each one must be a different substance. So we've basically separated out the different substances. However, if any of our chemicals aren't soluble in that solvent, then they won't be able to dissolve and move up the paper, so they'll just stay on the baseline. Once the solvent has almost reached the top of the paper, we take it out and leave it to dry, and the pattern of spots that we have left is called a chromatogram. Now, to explain why the different chemicals move up the filter paper at different rates, you need to use a couple of weird terms: the mobile phase and the stationary phase. What makes these things odd is you don't want to think of these phases as periods of time, but rather as types of substances. The mobile phase is a substance that the molecules can move in. It's always a liquid or a gas, and in our paper chromatography, it would be the solvent that we used. Meanwhile, the stationary phase is a substance or material that the molecules can't move in. So usually a solid, or sometimes a really thick liquid. But for us here, it would be our paper, During the chromatography experiment, the different chemicals in our sample of ink will constantly change between the mobile and stationary phases, dissolving in the solvent, moving a little bit, and then binding to the paper, over and over again. And so overall, how much time they spend in each of these two phases is going to determine how fast they move up the paper. With the chemicals that are more soluble in the solvent spending more time in the mobile phase, and therefore moving faster, and those that are less soluble, or are more attracted to the paper, spending more time in the stationary phase, and so moving more slowly. So if you think about it, how far each of the chemicals travels is dependent on the properties of that substance. And if we did the same experiment again, our chromatogram would look the same. This means that if we measure how far each substance moves, we can compare those values to a data book and identify which type of chemical it must have been. How far each of the chemicals moves, though, is also going to depend on how long we leave the experiment. So instead of comparing the actual distance, we instead calculate a ratio called the RF value, which is equal to the distance travelled by the substance divided by the distance travelled by the solvent. So if this pink substance had travelled 6 centimeters from the baseline, and the solvent had travelled 10 centimeters, then our RF value would be 6 divided by 10, so 0.6. One of the important things to appreciate with chromatography is that when we do chromatography with a pure substance, so a substance with only one type of chemical in it, then it won't separate out at all. We'll just get a single spot on our chromatogram, for which we can calculate a specific RF value. However, if we did the experiment again, with the same substance but a different solvent, or a different type of paper, then the chromatogram might look different. And our RF value would be different too, because we'd have changed the mobile or stationary phase. So when a chemist looks up an RF value in a databook, they'd have to take into account which solvent the experiment was done in, and what type of paper was used.
Next, I'll be talking about sieving. Sieving is used to separate solid particles of different sizes. The mixture is placed on the sieve with a mesh of a particular size. Particles smaller than the mesh size of the sieve will pass through the sieve, while the larger particles remain on the sieve. This method is used extensively in mining and Gary production. So you take notes. So this is an example of a sieve. So you take notes. Sieving can be used to separate sand particles of different size, sand and gravel. Next, we'll be talking about tests for purity. Once we have obtained a pure sample of a substance, we can use the following criteria to determine its purity. If the substance is a solid, then its purity can be checked by determining its melting point. This is because the melting point of a pure substance is fixed at a certain temperature. This temperature is only affected if impurities are present. If it is a liquid, its purity can also be checked by determining its boiling point. And this is because the boiling point of a pure substance is fixed at a certain temperature and can only be affected if impurities are present. For a pure substance, it gives one spot on a paper chromatogram.